All right. All right, so first thing we should probably do is define for ourselves what a matrix is. A matrix is nothing more than basically a table with rows and columns. So technically, Microsoft Excel spreadsheet is a matrix. Okay, that's all a matrix is.
I have a question real quick.
Yeah, go ahead.
Isn't there a way to put that into the calculator?
What's that? Matrices? Yeah.
Yeah, okay.
Yeah, we'll show you. Hopefully, we'll have a chance to show ourselves how to solve these systems using matrices on a calculator. Also. All right, now matrices in all textbooks that you'll ever look at are always denoted by uppercase letters. Okay, so suppose I define a matrix A to be this matrix here. Now this matrix we say has an order of a 2 by 2. All right, where the first 2 represents the number of rows that the matrix has, and the second entry represents the number of columns that the matrix has. So this is a 2 by 2 matrix. All right. Secondly, because the number of rows, which is equal to 2, is equal to the number of columns, we call this a square matrix. So a square matrix is a matrix where the number of rows is equal to the number of columns. Not all matrices are square, but this one is. Okay. So it has 2 rows by 2 columns. It's a 2 by 2 square matrix. We say that this notation here, lowercase a with a little subscript of 1, 1, is called the 1, 1 entry of the matrix. Or more specifically, it's the row 1, column 1 entry of the matrix. This entry here is the 1, 2 entry of the matrix, or the row 1, column 2 entry. Of our matrix. This is the 2, 1 entry, the row 2, column 1 entry. This is the 2, 2 entry, the row 2, column 2 entry. All right, so those are the entries of the matrix there. We say that the main diagonal of this matrix consists of the entries, the 1, 1 entry and the 2, 2 entry. So we call this the main diagonal of our matrix, the main diagonal, which consists of the 1, 1 and a 2, 2 entry. Okay. All right. Any questions so far here? A little bit of matrix terminology. Here's a matrix. All right, what would be the order of this matrix? How many rows by how many columns does this matrix have? It's 2 rows by 3 columns. So this is a 2 by 3 matrix. 2 rows, 3 columns. That's the 1, 1 entry, the 1, 2 entry, the 1, 3 entry, the 2, 1 entry, the 2, 2 entry, and the 2, 3 entry. This is not a square matrix. Because the number of rows does not equal the number of columns. And another thing is that non-square matrices do not have a main diagonal like square matrices do. Okay. All right, now, so what are we going to do with these matrices? Well, we're going to show ourselves ultimately how to solve systems of linear equations by using matrices. So the first thing that we would probably want to do is show ourselves how to represent a system of linear equations using a matrix. Any questions about any of this terminology on here?
Yeah, what would the main diagonal be for the second one?
Well, there really is no main diagonal for a non-square matrix
Okay.
unless it's what's called an augmented matrix. And I'm going to show you that in a second. All right, so suppose that I have this system of two linear equations and two unknowns. How could I represent this system of two linear equations and two unknowns using a matrix? Well, it's pretty simple to do. The first equation goes into the matrix by just indicating the coefficients on the right-hand side constant. So the first equation goes in as 2, 5, and we either have a vertical dashed line or a solid dashed line. Some textbooks have solid, some have dashed. That separate the left-hand side coefficients of the system from the right-hand side constants. So the first equation of this matrix goes into the first equation in the system goes into the matrix as the first row looking like this. The second equation goes in and becomes the second row of our matrix, which would be 3, -10, and -24. This matrix here is called a 2 by 3 augmented matrix. It's an augmented matrix because it pertains to a system of equations where we have the coefficients on the left side of this vertical line and we have the right-hand side constants of our equations over here. Okay. Technically, there is a main diagonal for augmented matrix. The main diagonal would be right here. These elements are lying on what's called the main diagonal, the 1, 1, and the 2, 2 entries here. All right, it is a non-square matrix overall, but because it's an augmented matrix and pertains to a system of equations, we would say that this is the main diagonal of the coefficient part of the matrix. And what if we had a system of 3 equations and 3 unknowns? Could we represent it using a matrix? The answer is absolutely yes. Here's an example, a system of 3 linear equations and 3 unknowns. And this is how it would be portrayed as a 3 by 4 augmented matrix. 3 by 4 augmented matrix. Notice there's no z variable in the first equation, so to represent the missing z variable, we have 0 for its coefficient. 0. Okay. So any questions how we are representing systems of linear equations by using matrices here so far?
For the main diagonal, is it always the top left and bottom right? For squared ones?
Yeah. So in general, what elements lie on the main diagonal? So if you have a square matrix, so if let's say that if A is a square matrix, then A sub ij is a main diagonal element or lies on the main diagonal if I equals j. You see that there?
Yeah.
So main diagonal elements are of a square matrix are always entries of a matrix where the row is equal to the column index. The row index equals the column index. So that's why for a square matrix, the 1-1 entry is on the main diagonal, the 2-2 entry, the 3-3, the 4-4, the 5-5, etc. Dot 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 all the way to the n entry. Okay. All right. So, and the main diagonal does go from the upper left to the lower right as you progress the elements on the main diagonal.
Okay, thank you.
All right, so far we've found out how to represent a system of linear equations using matrices, and you're probably wondering, you know, why use matrices? Why not just solve them the way we solved them in the past? Well, ladies and gentlemen, the answer in one word is computers. Computers can solve things a lot faster than we can solve things. But however, in order to teach a computer how to solve a system of equations, a computer programmer makes use of not matrices, but makes use of what are called arrays. In computer programming, a matrix is called an array. So arrays are the same thing as matrices. Computers work very nicely with arrays or matrices, and therefore it's a more streamlined way of presenting the problem to the computer system by using arrays or matrices, right? And so by being exposed to this, not only are we exposing ourselves to matrices, which are used for other things in higher level math, other than just solving systems of equations. So it is important that you're at least exposed to them. But of course, in linear algebra, you work with matrices all the time. All right, and also computer programming oftentimes has us enter problems in the form of a matrix and present it to the computer system. Okay, so it's important to touch base with matrices if you're in the computational field. Very important at least to be exposed to them. All right. Okay, that's great. Now we know how to represent systems of equations using matrices. But ladies and gentlemen, that's only the beginning of where we're going here. How do we, once we represent a system of linear equations using a matrix, how do we actually, solve the system using matrices? Well, to do that, we have to arm ourselves with what are called elementary row operations. Okay, and elementary row operations are best described in your textbook in section 6.1. So I am going to draw our attention to page 565 in our textbook. This is section 6.1, solving systems of linear equations using matrices. On page 565, we will begin to warm up to what are called elementary row operations. Okay. What are they? Well, stop and think. If I have a system of two linear equations and two unknowns, do you agree that it is perfectly legal to interchange any two equations in my system? Would I still not have an equivalent system if I interchanged equations 1 and 2? Isn't this system still the same as this one over here? So what? We interchanged our equations. We're still solving the same system. So this will lead us to our first elementary row operation or legal operation we can subject a matrix to, and that is we can always interchange any two equations in our system. Another valid operation when solving a system of linear equations is that we can always multiply an equation by a non-zero constant. In other words, suppose I take equation 1 and multiply both sides of it by 3. Well, guess what? I will produce an equivalent equation. Looks different, but it's still equivalent to the original equation. So 3x plus 6y equals 15 is still equal to x plus 2y equals 5. And there's one more legal operation. We can always add a multiple of one equation to another equation to produce a new equation. This is a legal thing that we've done when employing the elimination method in solving systems of equations. So in this case, they decided to multiply the first equation by 3 and then add it to equation 2 to produce a new equivalent equation called y equals 2. So these legal moves that we can subject a system of linear equations to are also going to be analogously the three legal elementary row operations that we can subject a matrix to that holds our systems of equations. So, ladies and gentlemen, suppose that I have a system of two linear equations and two unknowns. In fact, it's the system above here, the original system right here, entered in as a 2x3 augmented matrix. Do you agree that by interchanging two equations in that system, that's really equivalent to having interchanged rows 1 and 2? So one elementary row operation that is legal to subject a matrix to is we can always interchange any two rows. And by doing so, we still have an equivalent matrix, hence an equivalent system of equations being represented. A second valid elementary row operation. Up here, we've seen where we can multiply an equation by a non-zero constant and still have an equivalent equation, hence an equivalent system. Well, that translates into our second elementary row operation, which says I can always multiply any row of a matrix by a non-zero constant. Now, notice the notation up here, R1 and R2 with this bidirectional arrow in between them says that you're interchanging rows 1 and 2. This notation that says 3 times row 1, and then an arrow pointing to row 1 says that we're going to multiply row 1 of this matrix by 3 to produce an equivalent and brand new row 1. So every element of row 1 is getting multiplied by 3 to produce an equivalent row 1. So this matrix over here is equivalent to the original matrix back over here. The third valid operation on a system of equations had us adding a multiple of one equation to another equation, which is legal to do. Well, that translates into our third elementary valid row operation, which says I can always multiply a row of my matrix by a non-zero constant and then add it to some other row to produce a new row. So this notation is saying I'm multiplying row 1 by 3 and then adding those new entries to the corresponding entries of row 2 to produce a brand new row 2. So in this last elementary row operation, we're using row 1 to transform row 2. We're not changing row 1. We're using row 1 to change row 2 in an equivalent way. So this matrix over here to the right would still be equal to the matrix back over here. Do we understand these three elementary row operations? 3 of them. Okay, these are the 3 valid moves that you can subject a matrix to. If you try to do anything else other than these valid operations, then you're doing illegal mathematics to a matrix, okay? So 3 valid elementary row operations. All right, let's look at example 2. They give us a 3x4 augmented matrix that would pertain to a system of 3 equations and 3 unknowns. They want us to not only perform some elementary row operations on this matrix, but they want us to indicate what the new updated matrix would be after having performed the elementary row operation. What is this first elementary row operation having us do here in A? What is it saying to do here?
To flip them?
Yeah, we're going to flip what rows? Interchange what 2 rows?
1 and 2.
1 and 2. So rows 1 and 2 get interchanged or flipped. And we have a new equivalent 3x4 matrix over here. That's pretty simple, isn't it? That's an easy elementary row operation to undertake. All right, what does the second elementary row operation say we need to perform on this matrix? We need to multiply row 1 by a non-zero constant in the form of 1/4. And then we're using that product of that row and that constant to produce a new equivalent row 1. So the second elementary row operation is saying I'm going to multiply all the entries in row 1 of the original matrix by 1/4, and that will produce a new equivalent row 1. So 4 times 1/4 is 1. 3 times 1/4 is 3/4. 0 times 1/4 is 0. 5 times 1/4 is 5/4. Do we understand what happened with that elementary row operation there? The third elementary row operation, what's that? Is it
I was saying, yeah.
making sense? Okay, now the third elementary row operation says we're gonna multiply row 2 by -2 and then add the corresponding entries of row 3 to produce a new row 3. Notice we're not changing row 2, we're changing row 3, but we're using row 2 to help us change row 3. That is a valid elementary row operation. So what is this saying again? It's saying we're going to multiply all the entries in row 2 of the original matrix by 2. So 2 times 1 gives it, -2 times 1 gives us -2. -2 times 4 gives us -8. -2 times -1 gives us 2. -2 times 9 gives us -18. Then we're going to add the corresponding entries of row 3. And by doing that, by adding these values together, we produce a brand new row 3, an equivalent row 3. It doesn't look like it's equal to the original row 3, but it is. And the new equivalent row 3 would be 0, -8, -1, -26. Now we update our matrix after having performed that elementary row operation. This would be our new equivalent matrix over here. Notice row 2 has not changed. We used row 2 to change row 3. Only row 3 changed. So, ladies and gentlemen, are these making sense? These 3 elementary row operations that are subjected to a matrix in transforming a matrix into an equivalent matrix. All right, so those are the 3 elementary row operations that are going to be needed in order for us to be able to solve systems of linear equations using matrices here. Okay. Let's see what we got here. All right, now, so where are we going to go? I mean, but how are we actually going to solve systems of equations using matrices? You know, we know how to represent systems using matrices. We know about these elementary row operations, but how are we going to put this all together to actually solve systems? Well, ladies and gentlemen, there's 2 methods that enable us to solve systems of linear equations using matrices that we're going to look at today. The first technique has a name. It's called the Gaussian elimination method, in honor of a prominent German mathematician by the name of Carl Gauss. Carl Gauss came up with this technique. He's not alive today. He passed away many years ago, but this fellow came up with a brilliant technique called the Gaussian elimination method. There's another technique we'll also touch base with called the Gauss-Jordan elimination method here. All right. So what do both these techniques entail? Well, when we use the Gaussian elimination method, our ultimate goal is to get our matrix into what is called row echelon form. If you use the Gauss-Jordan elimination technique, your ultimate goal is to get your matrix into what is called reduced row echelon form. First of all, let's look at row echelon form. What does it mean for a matrix to be in row echelon form? Well, we say that a matrix is in row echelon form if it satisfies the 3 following conditions. Number 1, any row consisting of entirely all zeros must be or appear at the bottom of the matrix. That's a requirement. Number 2, for all other rows, the first non-zero entry we strike as we move from left to right in each row must be a 1. This 1 is called the leading 1 of the row. Number 3 requirement. The leading 1 in each non-zero row must be to the right of the leading 1 in the row that immediately preceded the row, or the row that is immediately above. You'll see what that's saying in a moment. Let's look at some examples of some matrices that are classified as being in row echelon form. We say that this matrix here is in row echelon form. Okay. Why? Well, as we proceed from left to right in each row, what's the first non-zero entry that we have to hit? We have to hit a 1. Do you agree? The first non-zero entry I hit moving from left to right in my first row is a 1. In moving from left to right in my second row, the first non-zero entry I strike is also a 1. So that requirement is satisfied. Notice this matrix does not have a row consisting of all zeros. If it did, that row would have to be at the bottom. So that requirement is satisfied. The only other requirement is this. Notice that the 1 that appears in row 2 is in a column that is to the right of the column that contains the 1 that appears in the previous row, namely row 1. That's to say, ladies and gentlemen, that for a matrix to be in row echelon form, all right, the leading ones of the rows have to be on the main diagonal of the matrix. In other words, for row 1, the leading one must be at the 1-1 entry, must be the 1-1 entry. For row 2, the 1 must be the 2-2 entry. If we had a row 3, the leading one would have to be the 3-3 entry, etc., etc., etc. This matrix here is in row echelon form. Notice the first non-zero entry you strike in any row from left to right is a 1. 1 here, 1 here, 1 here. Notice that the 1s are on the main diagonal, meaning that the 1 in row 2 is in a column that's to the right of the column that contains the 1 in row 1. The 1 in row 3 is in a column that's to the right of the column that contains the 1 in row 2. That's a part of the requirement of being in row echelon form here. So this matrix is in row echelon form. This matrix is in row echelon form. Notice the first non-zero entry we strike in a row, if it does have a non-zero entry, is a 1. Notice the 1s, okay. Basically, as we move from row to row, the 1s move 1 column further to the right. Notice we do have a row that consists of all zeros. Well, if we do, it must appear at the very bottom of the matrix. It does. And for that reason, all 3 of these things check out here. And that's why that matrix is in row echelon form. All right. So this is the form that we're striving to get our matrix looking like when we use the Gaussian elimination method to solving systems of equations. But how do we get our matrix looking like in this row echelon form? How do we get it into row echelon form? Well, we have to employ valid elementary row operations to achieve that. If, ladies and gentlemen, we're using the Gauss-Jordan elimination method, Gauss-Jordan requires that we get our matrix into an even more restrictive form called reduced row echelon form. What does it mean for a matrix to be in reduced row echelon form? Well, it says right here, a matrix is in reduced row echelon form if it is in row echelon form, with the added requirement that each row with a leading entry of 1 must have zeros above the leading 1. In other words, here are some examples of matrices that are in reduced row echelon form. This matrix here is in reduced row echelon form. Why? Because first of all, it's in row echelon form. So it satisfies all the 3 aforementioned requirements. But the added requirement to be in reduced row echelon form is that in row 2, above the leading 1, there must be a 0, and there is. The 1-2 entry is a 0. That's why we call this matrix reduced row echelon form. This matrix here is in reduced row echelon form because not only is this matrix in row echelon form, but it's also satisfying the requirement that above the leading 1 in each row, there must be zeros. That's why we say this matrix is in reduced row echelon form. This matrix here technically is in reduced row echelon form. Notice above the 1 in row 2, we have a 0. But why don't we have, okay, zeros in the third column above this 0 as the 3-3 entry? Well, because this is not a non-zero entry. This last row does not have any non-zero entry of 1. It's all zeros. As long as it appears at the bottom, then it doesn't matter if you have non-zero entries above this 3-3 entry of 0 here, because it's not a 1. But if this 3-3 entry was a 1 down here instead of a 0, then yes, these elements would have to both be 0 for this matrix to be in reduced row echelon form. If you had to guess, which one would require more work to get our matrix into? Row echelon form or reduced row echelon form? What would be your guess?
Reduced.
That's right. Reduced row echelon form has us going a couple of steps further. Getting the matrix into row echelon form is, in of itself is time consuming, but not as time consuming as it is to get the matrix all the way down into reduced row echelon form. But there's trade-offs. When you get your matrix into row echelon form, to find your coordinates of your ordered pair or ordered triple solution or whatever the case might be, you're going to have to use back substitution to arrive at your coordinates for your solution. If you get your matrix, however, in the reduced row echelon form, then the payoff is very handsome. The ordered pair or ordered triple or the solution in general will always appear in the rightmost column in that case. So there's trade-offs between both of these here. All right. How do you have your cake and your ice cream and eat them both? You use your calculator, because your TI-84 calculator can get these matrices into reduced row echelon form within a fraction of a second, okay, where it takes us maybe 10, 15, 20 minutes to do so. All right. Okay, so who can tell me why this matrix here is not in row echelon form? It's not in REF form. Why is this? Why is this matrix not in row echelon form?
There's no zeros above the ones in the second two columns.
Well, I'm just concerned about row echelon form, not reduced row echelon form. Okay. Remember, row echelon form is less restrictive than reduced row echelon form. What's the hang up here? Why this is not row echelon form? I got ones as my non-zero leading entries from left to right each. Well, do I? The first entry I strike in row 1 as I move from left to right in it is a 1. I strike a 1 as the first non-zero entry in row 2. But what's wrong with row 3? I don't strike 1 as my first non-zero leading entry. Because there's 3s here and this is not a 1, this matrix is not in row echelon form. Because remember, the first non-zero entry you have to strike in any row from left to right is a 1. Right? This ruins it. Why is this matrix not in reduced row echelon form? Reduced row echelon form. What's the problem? I strike a 1 from left to right as my first non-zero leading entry in each row. That's not the problem. And the 1s are in what? A column that's to the right in any subsequent row. No, but why is this not in reduced row echelon form? What is the problem? This matrix is in row echelon form. Don't get me wrong. It is in row echelon form, but why is it not in reduced row echelon form?
The 2.
That's this 2 right here. This is a problem. Because remember, to be in reduced row echelon form, it says that all the entries above the leading 1 of a row have to be 0. So here's your leading 1 of row 3. These entries would have to both be 0 for this to be in reduced row echelon form. So that's the problem. That's why this is not in reduced row echelon form. Okay. Is this making any sense here? There's no what it means for a matrix to be in row echelon form. Here's some more examples of matrices that are in row echelon form. All of these are in row echelon form. All of these matrices are in row echelon form. all of these matrices are in reduced row echelon form.
Can you go back up to the top one for 1 sec?
These are all in row echelon form there.
Thanks.
So these are in row echelon form. And these matrices down here are in, do we all have that there? All right, and these are all in reduced row echelon form. There. All right, and this is being recorded, so you do have the luxury of, you know, pausing this video and just kind of eyeballing these and running through your mind at your leisure. That's one nice thing about having videos. All right. Okay, so ladies and gentlemen, how are we going to solve, you know, these systems of equations using this, you know, this Gaussian elimination to get our matrix into row echelon form, or the Gauss-Jordan elimination to get our matrix into reduced row echelon form? How are we going to do it? Well, this is not in your textbook, so you want to make sure that you know that this is a part of the video here. I have written out the steps in order as to how we take a system of two linear equations and two unknowns, write it as a 2x3 augmented matrix, and then using elementary row operations, how to get our matrix into row echelon form. So using the Gaussian elimination method, how do we get our 2x3 matrix into row echelon form? Well, step number one, you have to make sure the 1-1 entry of your matrix is a 1. This can be achieved a couple of different ways. Sometimes it's good enough just to interchange two rows of your matrix to accomplish this. But sometimes that doesn't work. Sometimes you may have to multiply row 1 by a non-zero constant to force 1 in the 1-1 entry. So your row 1, column 1 entry of your matrix must be a 1. That's how you kick this off. Once your 1-1 entry is a 1, then you move to step 2. Step 2 says, we have to then use row 1 to make all the entries below the 1-1 entry in column 1 become all zeros. I like to kind of shorten this up and say we use row 1 to clear out the rest of column 1 below the main diagonal. All right. And you'll see how all these steps play out with examples. Right now, they may not mean too much to you, but you'll see how it all comes into focus. How do we normally clear out the rest of column 1 below the main diagonal? When the 1-1 entry is 1 and by using row 1? Well, we normally add a multiple. We normally add a multiple of row 1 to rows 2 and 3 and 4, and however big our system is, to basically clear out the rest of column 1. Once we clear out the rest of column 1, we're done using row 1. Now we have to make sure our 2-2 entry becomes a 1. That's the next step. And to accomplish that, we normally have to multiply row 2 by a non-zero constant to achieve that. So we have to make the 2-2 entry, the row 2, column 2 entry on the main diagonal. We got to make that entry become a 1. That's the next thing. Once we make the 2-2 entry a 1, we're then going to use row 2 to clear out the rest of column 2 below the main diagonal. That's to say that we need to make all the entries below the 2-2 entry in column 2. We need to make all those entries become 0. To do that, we normally add a multiple of row 2 to like row 3 or row 4 or row 5, however big our system is. But I'm only going to show you how to solve up to systems of 3 equations of 3 unknowns using matrices here manually. I'm not going to have you solving systems of 4 equations of 4 unknowns manually, or 5 equations, 5 unknowns manually. Okay. If we get in those real big systems, we normally turn them over to a computer system. All right, so once we clear out the rest of column 2 below the main diagonal, then, because remember, this was a system of 2 equations, 2 unknowns, essentially we're almost done. All we have to do is use what's called back substitution to recover our x and y coordinates of our ordered pair solution. If this was a system of 3 equations and 3 unknowns, ladies and gentlemen, we have to just continue going onwards. So after clearing out the rest of column 2 using row 2, the next step would be to make the 3 entry become a 1. And then use row 3 to clear out the rest of column 3, etc., etc., etc. Okay. All right. So this is about as clear as mud right now in your mind. But with examples, this will all hopefully start to come into focus as to what these steps are really saying and the order in which we are to pursue them. All righty, so why don't we just look at an example? I'll walk through a couple of examples and show ourselves how to solve systems of 2 linear equations and 2 unknowns using the Gaussian elimination method. Okay. All right, any questions about any of these steps here? All right, so here we go. All right, so we're going to try to solve by Gaussian elimination. Now, because this is a virtual course, ladies and gentlemen, I mean, I can't police over you and make sure that using the Gaussian elimination method of solving these systems. Some of you might just cut corners and say, I'm just gonna, use the elimination of the substitution method we learned earlier. But don't cheat yourself, because there will be questions which will force you to demonstrate your knowledge of using elementary row operations anyways. So I would definitely probably just try to exercise and demonstrate the technique that's being, requested. I think that's a wise thing to do, especially if you're going onwards in the math. It's very important, ladies and gentlemen, to try to be able to do these techniques, okay? Be able to succeed at these techniques. All right, so here we go. Here's our system of 2 linear equations and 2 unknowns. There's the first equation, and here comes the second equation. So I want to solve the system of 2 linear equations, 2 unknowns by using Gaussian elimination. That's what we're going to try to do here. All right, what's the first step? The first step is we have to represent the system of 2 equations using an augmented matrix. So the first step is we have to write this system in the form of a 2x3 augmented matrix. Here's the first equation as the first row, and here's the second equation as the second row. That's pretty easy to do. There's your system in the form of a 2x3 augmented matrix. Now it's our goal to take this matrix and to reduce it down into row echelon form. That's our goal. How do we do that? Well, we pursue the steps that I just indicated here. We take them in the order in which I listed them. Step number 1, we have to make the 1, 1 entry become a 1. Right now, the 1, 1 entry is not a 1, it's a 2. Does anybody know what valid elementary row operation I can use to force the 1, 1 entry to become a 1? What could I do? How can I make the 1, 1 entry become a 1?
You could flip them.
All right, I would flip what rows? Well, we only have 2 rows, don't we? So I will interchange rows 1 and 2. Please do use this notation. Get in the habit of using this notation, because that helps you and the reader looking at your paper as to exactly what you just did. So let's interchange rows 1 and 2. Let's now update our matrix. This would be your equivalent matrix after performing that valid elementary row operation. There you go, ladies and gentlemen. That's your equivalent updated matrix there. All we did was interchange rows 1 and 2. Good. Now the 1, 1 entry is a 1. What's the next step? The next step now is using row 1. We're going to clear out the rest of column 1. What does that mean? Using row one, I have to make the other entries in the column one below the main diagonal become zeros. I gotta make this 2 become a 0. That's called clearing out the rest of column one below the main diagonal. What do you add to 2 to make this 0? What do we add to 2 to make 2 go to 0?
-2.
-2. Where are we going to get a -2 from? We're going to get
Multiply the whole equation by -1.
multiply which equation?
Would you like multiply the second row by -1? Is like, do you apply
Well,
those?
no, if you multiply the second row by -1, you're just going to have a -2 here. And you're going to have a what? A -2, correct? It's still not going to be 0. We got to make this 0. All right. No, multiply the second row by a non-zero constant is not going to work. I'm going to have to use row 1 to help me make this become a 0. So you said I had to add -2 to 2 to make this 0, correct? Where are we going to get the -2 from? Here's where we're going to get it from. I'm going to multiply row 1 by -2, then add it to row 2 to form a brand new row 2. That's a valid elementary row operation. So what am I going to do again? I'm going to take row 1, multiply it by -2, add that to row 2, then to produce a brand new row 2. That's a valid elementary row operation. You can always add a multiple of one row to another row to form a new row. So that's what we're going to do. So I'm going to take -2 times row 1. To that, I'm going to add row 2 to do what? To produce a new row 2. So I like to put a little -2 outside here next to row 1. Now this -2 is going to get multiplied into all these entries. What's -2 times 1? -2. What's -2 times 4? -8. What's -2 times -14? 28. Underneath there, we slide row 2. 2, 3, -13. Now we add these elements together. -2 plus 2 makes the 2, 1 entry become a required 0. -8 plus 3 is -5. 28 plus -13 is going to be 15. Guess what? There's your new brand new equivalent row 2. Let's update our matrix. I did not change row 1. I used row 1 to change row 2. So you pencil back in row 1 unaltered. Row 2 now takes on this new equivalent look. 0, -5, 15. Any questions with how I got to here so far? Our matrix has been updated to this now. We're getting closer to row echelon form. All right, now we're done clearing out the rest of column 1 below the main diagonal. Now the next move is we got to make the 2, 2 entry become a 1. The 2, 2 entry must become a 1. Ladies and gentlemen, how do I make this 2, 2 entry, which is a -5, become 1 by using a valid elementary row operation? How do I make this become 1?
Multiply the top one. I mean, just subtract the top one by the bottom one. Oh, that'd be make it negative.
I'll tell you what, why don't we just multiply the second row by the reciprocal of -5? What's the reciprocal of -5? -1/5. Let's multiply row 2 by -1/5 to form a new equivalent row 2. Remember, that's a valid elementary row operation. You can always multiply any row by a non-zero constant to form a new equivalent row. So we're going to multiply row 2 by -1/5. So what's -1/5 times 0? The 2, 1 entry remains as a 0. -1/5 times its reciprocal -5 is 1. -1/5 times 15. What is -1/5 multiplied by 15? Those darn fractions. That gives you -15/5, which is -3. This will be -3. There's your new equivalent row 2 here. Now, I want to get back to what you indicated earlier. You were saying like multiply row 1 by some non-zero constant, add it to row 2 to make this become a positive 1 here. Now, if you did that, here's the complication you would have. You would be multiplying this 1 by that non-zero constant and adding it to the 0, and you would destroy this 0 here that we worked so hard in the previous step to achieve. Do you agree? Remember, this element has to be a 0. So if you multiply row 1 by some constant, add it to row 2 to make this become a 1, I'll bet dollars to donuts that this entry is going to disappear as 0 and become a non-zero entry, where it has to be a 0 entry. That's the problem with that move. That's why it's better just to multiply row 2 by the reciprocal of -5 to force a 1 in the 2-2 position, okay? Because this remains as 0. All right, let's update our matrix now. So our new equivalent matrix, notice row 1 does not change. Row 2 undergoes yet another equivalent transformative change. It now takes on this look here. All right, there we go. Now, what's so big about this matrix here, ladies and gentlemen? What form is this matrix in? This matrix is in what form? REF or RREF? Is it in reduced row echelon form or row echelon form? Well, with inspection, we can see that this matrix is in row echelon form. Now that it is, we basically can recover our X and Y coordinates of our ordered pair solution. This is the X column coefficients, the Y column, and this is the right-hand side constants. From the first row, we generate this equation, 1x plus 4y equals -14. From the second row, we generate this equation, 0x. Now, when I say 0x, that means the x does not appear. 0x plus 1y, so we have 1y is equal to -3. Guess what? Our y coordinate of our ordered pair solution is -3. To get our x coordinate of our ordered pair solution, we have to back substitute this -3 up into the first equation and for the variable y. So the -3 goes in for y here. Upon making that substitution, I can solve this first equation then for x. Now we solve for x. So x minus 12 equals -14. Add 12 to both sides. And we get x is equal to -2. And we're done. Ladies and gentlemen, our ordered pair solution is -2, -3. That's it. So we have solved that system of 2 linear equations and 2 unknowns using the Gaussian elimination method. This is the Gaussian elimination method. Any questions how using valid elementary row operations, we got our matrix into row echelon form, and then by using back substitution, we were able to recover our coordinates for our ordered pair solution. Any questions there? Not making any sense at all what just happened there. Okay. All right, maybe I could try another one. Wait a minute, what time is it? All right. Always fighting the clock. All right, I'll try another one, okay? Let's try another one. Solve by Gaussian elimination. All right, step number 1, we have to represent the system using a 2x3 augmented matrix. So here we go. There's my system of 2 equations and 2 unknowns as a 2x3 augmented matrix. Okay, what's step number 1? Gaussian elimination, we gotta make the what? The 1 entry has to become a 1. So how do I achieve that? How do I make this 1 entry become a 1 here? What elementary row operation can I use? Make the 1 entry become a 1. Just interchange rows 1 and 2. That'll be good enough. All right, let's update our matrix now. Having done that. All right, now that the 1 entry is a 1, we're going to use row 1 to clear out the rest of column 1. So I'm going to make this 2 entry become a 0. To do that, I must add 3 to -3. Where am I going to get the 3 from? I'm going to get the 3 from by multiplying row 1 by 3, adding it to row 2 to form a new row 2. That's what we're going to do. Valid elementary row operation. I'm going to multiply row 1 by 3, add to that the corresponding entries of row 2 to form a brand new row 2. So here we go. What's 3 times 1? 3. 3 times -3, -9. 3 times a -16, -48. Underneath here, I slide row 2, -3, 11, 58. Add these rows together now. And we form a new row 2. The new 2 entry is going to become a 0. Adding these together, the 2 entry becomes 2. The 2 entry becomes 10. There's your new brand new equivalent row 2. Let's update our matrix. All right, our matrix is starting to take shape. It's moving closer to row echelon form. There's only one more step that I have to employ to get this into row echelon form. Does anybody know what that is? What must we do to get this into row echelon form? One more move. One more move. Riley Collette, would you have any idea whatsoever as to what the last move I have to make here on this matrix?
He used a substitution to solve for the ordered pair.
Well, we're not there yet. I gotta make this entry.
Oh,
become-
use row 2 to make all entries.
Well, I gotta first of all make this entry become a what? The 2 entry has to become a
0
no, not a
or
0.
a one. I'm sorry.
Right here. 2 entry must become a what? 1.
A
Right
1.
there now,
Yeah,
right?
sorry.
So how am I gonna make this 2 entry become a 1? Can I just erase the 2 and put a 1 here? Yeah, you can do anything you want, but it's not legal. It's not valid. How do I make this become a 2 and still maintain an equivalent matrix, an equivalent system?
Make another operation with the -3 up top.
Okay, now here's the problem. And you're not alone. A lot of students like to do this. They like to think that, well, I'm going to multiply row 1 by some multiple and then add it to row 2 to force this to become a 1. But now look at, here's the problem when you do that. If you multiply, this entry by a non-zero constant, you got to multiply all the entries in row 1 by a non-zero constant and then add them to the corresponding entries of row 2. If you add this 1, if you multiply this 1 by a non-zero constant and then add it to this 0, this entry is not going to be 0 anymore. We will have destroyed what we did back over here to make this entry become a 0. Do you see that there? You don't want to undo what we've done here, all right? And by adding a multiple of row 1 to row 2, you're going to make this entry become non-zero, which we will have defeated what we just did from here to here. Okay, so no, you don't want to do that. We want to make sure this remains as 0, this entry. Okay, but we want this to become 1 though. The only way that's going to happen is if we multiply row 2 by a non-zero constant. And what do you multiply 2 by to make it 1?
1/2.
1/2. It's reciprocal. So here we're going to do that. We're going to multiply row 2 by 1/2 to form a new row 2. Not only will this make this 1 now in doing that, but this is going to keep this 2 1 entry as a 0. Very important. All right, so let's do that. So when I multiply row 2 by 1/2, what new row 2 do I get? 1/2 times 0 is 0. 1/2 times 2 is 1. 1/2 times 10. 1/2 of 10 is 5. This is going to be my new row 2. So let's update our matrix now. So my new row 2 is going to be 0, 1, 5. Now this matrix is in what form? That's row echelon form, correct? So now we should be able to recover our X and Y coordinates for our ordered pair solution. From the first row, we get what equation? Remember, this is your X column, Y column, and this is your right-hand side constant column. So from the first row, we get the equation 1x minus 3y equals -16. The second equation gives me, second row gives me what equation? 0x plus 1y, so we have 1y equals 5. There you go. Your y coordinate is 5. Now to find the x coordinate, we take 5 and back substitute it into the first equation and for y. Upon making that substitution, the equation becomes x minus 3 times 5 equals -16. X minus 15 equals -16. Add 15 to both sides. And therefore, x is equal to what? -1? And ladies and gentlemen, we're done. Our ordered pair solution is -1, 5. This is called Gaussian elimination. Gaussian elimination here. Again, not only am I hoping that you've been doing this throughout the whole semester of looking at examples in your textbook of sections that I cover, but it's going to become even more important, probably, especially for this section, to get this procedure down, this Gaussian elimination, to look at all the examples in that section 6.1. Make sure you go over them, study them carefully. It's only going to complement what I'm trying to push here during this class session, okay? So very important to go back and also look at some of the examples in your textbook. Very, very important. It'll hopefully, you know, further ingrain this more firmly in your mind. Okay, ladies and gentlemen, I've been using up to this point the Gaussian elimination method. What if I wanted to solve this same system right here by using not the Gaussian elimination method, but what if I wanted to use the other technique, the Gauss, anybody remember the other name, the other technique?
Jordan.
The Gauss-Jordan method. What if I wanted to solve this same system using the Gauss-Jordan method? I should get the same answer. What's the only difference? Anybody know the difference? There's only one little difference. What if I wanted Gauss-Jordan method to be employed instead of Gaussian elimination? Well, for the Gauss-Jordan method to be used, we have to make sure that our matrix is reduced not only down just to row echelon form, but we have to go a little further. We have to reduce this down into reduced row echelon form. But the good news is this: any matrix that is in reduced row echelon form, first of all, is in row echelon form. It's just that it has that one added requirement that you cannot have any non-zero entry above a 1 of any row. So ladies and gentlemen, I can pick up where I left off right here. You see that right here? I can pick up with this matrix that's in row echelon form, and I just have to do one more thing to it to get it into reduced row echelon form. Does anybody know what that one thing is to get this matrix from row echelon form into reduced row echelon form? What's the only other move I got to make?
Get the -3 is 0.
That's right. This -3, which is above the leading one of row 2, has got to become 0. This must become 0 for this matrix to be in reduced row echelon form. That's the only other move we got to make. And we will have basically solved this using Gauss-Jordan method. okay? Well, how do I make this -3 become a 0? Well, ask yourself, is it good enough? I mean, we got to add 3 to it, but where are we going to get the 3 from? Where am I going to get the 3 to add to this -3 to make this 0? Where's it going to come from? What valid elementary row operation is going to enable me to form a 3 or to get a 3 somewhere and to add it to this -3 to make this 0? What am I going to do here? Where do I get my 3 from to add to this?
Multiply the bottom one by 3.
That's right. We're going to use row 2 to transform row 1. Specifically, I'm going to multiply row 2 now by 3, add it to row 1, and that'll make this go to 0. And this entry will still remain as a required 1, because when you multiply this by 3, this is 0. 0 plus 1 keeps the 1 entry as a 1. That is also very important that remain a 1. Okay, so here we go. We just got one more step here, one more elementary row operation to get this thing into reduced row echelon form. So I am going to pick up where we left off. Pick up with my row echelon form to now take this one step further to reduced row echelon form. And to do that, all I got to do, you said, is to make this 0, which means I'm going to multiply row 2. Wait a minute. I got to multiply row 2 by 3, add that to row 1 to produce a new row 1. That's what we need to do. That's a valid elementary row operation. So 3 times row 2's entries added to the corresponding row 1 entry to form a new row 1. What's 3 times row 2's entries? 3 times 0 is 0. 3 times 1 is 3. 3 times 5 is 15. Slide row 1 underneath here. 1, -3, -16. Now add these entries together. Hence we get 1, 0, and -1. Ladies and gentlemen, this is your brand new row 1. Brand new equivalent row 1. Let's pencil it in. Updating our matrix. We got row 1 now as being 1, 0, -1. Row 2 is 0, 1, 5. Now what form is this matrix in? This is now in reduced row echelon form. Now here's the beauty of having gotten this matrix into reduced row echelon form. Yes, it entailed one more elementary row operation, more work to do so, but the payoff is very handsome. Because, ladies and gentlemen, what equation does my first row give me now? 1x plus 0y equals -1. In other words, 1x equals what? -1. That's your x coordinate. The second row gives me what equation? 0x plus 1y equals 5. In other words, 1y equals 5. We're done. Look at that. In other words, your solution appears in the rightmost column. You can just read it off. That is your ordered pair solution. There's your x coordinate. There's your y coordinate. See the nice thing about getting your matrix into reduced row echelon form? Yes, it's more work, but the payoff in the end is extremely attractive. We get the same solution of -1, 5. We don't have to do any back substituting like we did when we got our matrix into row echelon form. With row echelon form, we had to what? We had to back substitute the 5 up into the first equation for y to solve for x. You see that little extra work there? So there's good and bad with the row echelon form as opposed to reduced row echelon form. There's good and bad between the Gaussian elimination method versus the Gauss-Jordan elimination method, or the Gauss-Jordan method, excuse me. All right, so both methods have their pros and cons. Do we understand we got the same solution, whether we use Gaussian elimination or we took it down further and used Gauss-Jordan, got this down to reduced row echelon form. Same solution. All right, the time has come, ladies and gentlemen, because time is burning here. I need to demonstrate for you how to solve a system of 3 linear equations and 3 unknowns using Gaussian elimination. Now, I am not going to require that you manually demonstrate Gauss-Jordan method for a system of 3 equations and 3 unknowns. I may for a system of 2 equations and 2 unknowns, but not for a system of 3 equations and 3 unknowns. But I may have you solve a system using Gaussian elimination for a system of 3 equations and 3 unknowns. But not Gauss-Jordan, not manually. So we're going to try to solve this system of 3 linear equations and 3 unknowns using the Gaussian elimination method. Remember in the past, back in chapter 5, we had you solving this bigger system using the elimination method by pairing up equations. You remember that technique? But now we're going to use matrices to solve the system of 3 linear equations and 3 unknowns for its ordered triple solution. So I'm going to walk through this using the Gaussian elimination method to show ourselves how we solve this slightly larger system of equations here. First, we have to write this system in the form of a 3x4 augmented matrix. Here's the first equation. Here's the second equation. Now, keep in mind, if you were missing any variables in any equation, you got to enter in 0 in place of those missing variables. Here's the third equation. And there you go. Our system now has been presented as a 3x4 augmented matrix. Ladies and gentlemen, the way we solve the system of 2 equations, 2 unknowns, Gaussian elimination works the same way as a system of 3 equations and 3 unknowns. It's just that we have 1 more column to deal with and 1 more row to deal with. That's the only difference. So what do you think step number 1 will be? We need to make the 1 entry become a what? Same thing, you start at the same place. We got to make the 1 entry become a 1. That's how we kick this off. How can I do that validly? What elementary row operation will enable me to put a 1 there? You actually have many options. You could multiply row 1 by 1/2. That would force a 1 in the 1, 1 position. We don't need to do that though. Can I not interchange either rows 1 and 2 or 1 and 3 to force a 1 in the 1, 1 position? Let's use one of those. I'm going to interchange rows 1 and 2. That's my decision. You could have just as well have decided to interchange rows 1 and 3. Same thing. Don't worry about it. Both ways would work. Either way is valid. So row 1 becomes row 2. And row 2 becomes row 1. Row 3 remains as row 3. All right, good. Now the 1, 1 entry is a 1. The next step. Now we have to use row 1 to clear out the rest of column 1. So I got to use row 1 to make this entry become a 0 and this entry become a 0. What do you add to 2 to make it 0? -2. So to make this entry become a 0, I'm going to multiply row 1 by -2 and add it to row 2 to form a new row 2. In other words, I'm going to multiply row 1 by -2, add it to row 2 to form a new row 2. In a similar fashion, I got to make this entry become a 0. I need to add -1 to it. Where am I going to get the -1? I'm going to multiply row 1 by -1 and add it to row 3 to form a new row 3. So I'm going to multiply row 1 by -1, add it to row 3 to form a new row 3. So I got to do 2 elementary row operations to clear out the rest of column 1 instead of 1 elementary row operation that we employed with a system of only 2 equations and 2 unknowns. He's got a little extra work to do, that's all. All right, so let's do this one first. -2 times row 1 added to row 2 to form a new row 2. What's -2 times row 1? -2 times 1 is -2. -2 times -2, +4. -2 times 14, -28. -2 times -1, +2. Slide row 2 underneath this. Now add the entries together. This becomes 0. This becomes -4. What's 54 minus 28? 26, is that correct? 26. And 2 plus a -4 is -2. There's your new equivalent row 2. We can update our matrix. Which row is not changing here? Which row is not changing? Going from here to here. What's that now? Which row is not changing going from here to here? Which row am I not changing?
Row 3.
Well, no, I'm going to be changing rows 2 and what? Rows 3. But what row will not change?
Row 1.
Row 1. I'm using row 1 to change row 2 and row 3. But row 1, it does not change. Just pencil back in row 1. All right, now row 2 is about to take on this new equivalent look. Here's my new equivalent row 2. 0, -4, 26, -2. Now we need to change row 3 using row 1. Specifically, I'm going to multiply row 1 by -1, add it to row 3 to produce a new row 3. So here we go. -1 times row 1 entries added to row 3 to produce a new row 3. What's -1 times row 1's entries? -1 times 1, -1. -1 times -2, +2. -1 times 14, -14. -1 times -1, +1. Slide row 3's entries underneath this. Now add the rows together. My new 3-1 entry becomes a 0. 2 plus a -3, the new 2 entry becomes -1. The 3-3 entry becomes a 5, and the 3-4 entry becomes a -2. There's my new equivalent row 3. Pencil that in for row 3. My matrix has been updated to looking like this. Ladies and gentlemen, I'm done using row 1 to clear out the rest of column 1 below the main diagonal. We're done with that. Does anybody know what the next step is now? What's the next step? Do we remember? The next step is to make the 2-2 entry become a what?
0
No, not 0.
or 1, a 1. I'm sorry. I keep doing that.
You're always off by 1 digit.
I know. I'm sorry.
All right. We got to make this become a 1. Now, how can I do that? Well, what you don't want to do is you don't want to multiply row 1 by some non-zero constant and add it to row 2 to make this 1. Because if you do that, you're going to destroy this 0 here. This will become a non-zero entry when in fact it must remain 0. So we don't want to do what we did here. We want to keep this as a 0. No, the easiest way to make this become a 1 is just multiply row 2 by the reciprocal of -4. Just multiply the row 2 by -1/4. So let's do that. So I'm going to multiply row 2 by -1/4 to form a new row 2. That's what I'm going to do. Multiply row 2 by -1/4 to form a new equivalent row 2. And then I will be able to update my matrix. Notice I'm not changing row 1. And I'm not changing row 3 this time. I'm only changing row 2. So you want to pencil back in rows 1 and 3. All right, row 2 is about to undergo a facelift. What is -1/4 times 0? That keeps the 2-1 entry as a 0 as it needs to remain. What's -1/4 times -4? -1/4 times -4 makes the 2-2 entry become a required 1. What's -1/4 times 26? Uh-oh. Now we're starting to see something that we've never seen before. Is it possible when you're using these elementary row operations to generate fractions? The answer is yes. Get used to it. It happens all the time. So -1/4 times 26 is gonna give me what? Negative 26/4. What you don't want to do, ladies and gentlemen, is turn your fractions into decimals. Don't do that. You think fractions are messy. Decimals are a nightmare. Never turn your fractions into decimals when using Gaussian elimination or Gauss-Jordan. Always leave them as fractions. You can reduce them, but leave them as fractions. This can reduce, by the way, down by 2 to negative 13 halves. All right. So that's going to be my new 2-3 entry, negative 13 halves, after having multiplied this by negative 1/4. Negative 13 halves. Now you want to multiply negative 1/4 by negative 2. And what is negative 1/4 times negative 2? Well, that's going to be positive 2/4, but positive 2/4 reduces down to 1/2. That's my new 2-4 entry, 1/2. That's my new updated matrix. We're getting closer to row echelon form. Slowly but surely, we're getting closer. What do I got to do next? Remember, we're shooting for row echelon form, ladies and gentlemen. What do I have to do next? What do I got to do next to get this into row echelon form?
Make the third row -1 a 0.
Yep, we're going to now use row 2. Now that we made the 2-2 entry become a 1, we use row 2 to clear out the rest of column 2 below the main diagonal. We got to make this -1 become a 0. And to do that, we have to add 1 to it. Where are we going to get the 1? How about just multiply row 2 by 1 and add it to row 3 to form a new row 3? Or technically, you could just say add rows 2 and 3 together to form a new row 3. So we're going to add row 2 to row 3 to form a new row 3. All right, let's do that. Let's update our matrix now. Notice I'm not changing row 1. Am I changing row 2 from here to here? Am I changing row 2? No, I'm changing row 3. I'm using row 2 to update or change row 3, but row 2 does not change from here to here. Pencil back in row 2. All right, now we're going to change row 3 by adding row 2 to the elements of row 3. So 0 plus 0 keeps the 3-1 entry as a 0. And it must remain as a 0. We worked hard to make that a 0 way back. 1 plus a -1. What's 1 plus a -1? Now the 3-2 entry becomes a 0 as we require it to be. Now what's negative 13 halves plus 5? Oh no, not another trip back to basic math. What's negative 13 halves plus 5? Well, isn't that negative 13 halves plus 10 halves? Isn't that really negative 3 halves? Negative 3 halves. So negative 13 halves plus 5 is negative 3 halves. Negative 3 halves. What's 1/2 plus negative 2? 1/2 plus negative 2. Oh no. 1/2 plus a negative 2. Isn't that really 1/2 plus a negative 4 halves? Right? Which is really negative 3 halves. So 1/2 plus negative 2 is negative 3 halves. Negative 3 halves. Ladies and gentlemen, our matrix now looks like this. We're getting closer to row echelon form. There's just one more thing we have to do, and this will be in row echelon form. What is that one more thing? What's the one more thing we got to do on this?
Plug everything back in.
Well, we're not ready for back substituting, not ready for that business. No, there's just one more elementary row operation. One more entry has to be tweaked for this to be in row echelon form. What is that entry?
In row 3, you have to have the -3-2-0-1.
Yeah, the 3-3 entry now, the 3-3 entry must become a 1. We got to make this guy become 1. How do we do that without disrupting any of these other things here? We want these to remain as zeros. We don't want to mess around with these. How do I make this just become 1 and preserve all these zeros? How about just multiply row 3 by 1? The reciprocal of negative 3 halves. Multiply row 3 by negative 2/3 to produce a new row 3. That's all we have to do. That's a valid elementary row operation. You can always multiply any row by a non-zero constant. That's what I'm going to do here. So let's update our matrix, having done that. So going on to another piece of paper. Notice I'm not changing row 1. And I'm not changing row 2. But I am about to change row 3. All right. What's negative 2/3 times 0? 0. What's negative 2/3 times 0? 0. What's negative 2/3 times its reciprocal negative 3/2? 1. What's negative 2/3 times negative 3/2? Negative 2/3 times negative 3/2? 1. Ladies and gentlemen, what form is this matrix in now? That's called what? Row echelon form. Everybody see that there? That's row echelon form. That's row echelon form. Now, by back substituting, we can recover our X, Y, and Z coordinates for the ordered triple solution to this system. There's my X column, my Y column, my Z column, and my right-hand side constant. From the first row, what equation do I generate from my first row? 1x minus 2y plus 14z is equal to -1. From the second row, what equation do I generate? 0x plus 1y minus 13/2 z equals 1/2. From the third row, what equation do I generate? 0x plus 0y plus 1z equals 1. What's my z coordinate of my ordered triple solution? 1. That's your z coordinate. To find your y coordinate, we have to back substitute this 1 up into the second equation for z and then solve for y. So upon making this substitution, our second equation presents itself as y minus 13/2 times 1 equals 1/2, which means y minus 13/2 equals 1/2. Adding 13/2 to both sides, y is equal to 13/2 plus 1/2. Y is equal to 14/2. But what's another name for 14/2? What's another name for 14/2? 7. So now we know y is equal to 7. We got our y coordinate. Now to find our x coordinate, we're going to back substitute up in the first equation. What drops in for z? 1. What drops in for y? 7. And now we'll solve this equation for x. So after back substituting, our first equation becomes x minus 2 times 7 plus 14 times 1 equals -1. We solve for x. Going through the arithmetic, what's x going to be equal to? -1. And ladies and gentlemen, we're done. We have our ordered triple solution. -1, 7, 1. Done with problem. Everybody see that there? We're done. This technique is called what method? It is called Gaussian what? Gaussian elimination for solving a system of 3 linear equations and 3 unknowns by using elementary row operations and reducing our matrix down into row echelon form, and then by using back substitution, recovering the x, y, and z coordinates for the ordered triple solution. You see that there? All right, let's have some fun now. That was a lot of work. Let's try this same system with our TI-84 calculator now. So ladies and gentlemen, I'm going to enter this same system of 3 equations, 3 unknowns into my TI-84 calculator as a 3x4 augmented matrix. So let's go to our calculator now. bring up the TI-84 and I am going to show ourselves, hopefully, how to solve this system using the calculator. What just happened? Okay, my mouse is on the blinks here. I need another, somebody do me a favor. Catch me a mouse and give me a mouse, okay? All right, here we go, Liz Owen. Oops, we don't want that. What am I doing here? All right, so here we go. How do we enter the system in the form of a matrix? We have to go into matrix mode. Above your X to the -1 power key right here, which is the button just below your math button, above it, there's the word matrix. This is called your reciprocal button, by the way. So to access the function matrix, we have to hit our second key first, followed by our X reciprocal button. That takes us into our matrix mode. Go over to edit. Matrix, edit. Now hit enter. Now we need to establish how many rows by how many columns our matrix is to be. This is to be a 3x4. So you type in 3, enter, 4, enter, a 3x4 augmented matrix. Now we're going to type in the system here. So I'm going to type it in now. We got 2, -8, 54, -4. Second equation is 1, -2, 14, -1. Third equation goes in as 1, -3, 19, -3. Now, ladies and gentlemen, we have our system entered in the form of a 3x4 augmented matrix. We can have our calculator solve this system within about a fraction of 1 second. Okay? Your calculator is a little bit faster than we are. You've seen how long it took me to solve it manually, right? This is just a system of 3 equations, 3 unknowns. Can you imagine solving massive systems of hundreds of thousands of unknowns and hundreds of thousands of equations? Your weather forecasts are produced every day by having supercomputers solve massive systems of equations. But our computers that can crank out 20 trillion up to trillions and trillions of calculations per second still requires 30 minutes of nonstop crunch time to generate a 48-hour forecast, weather forecast for the Northern Hemisphere. That's how involved the mathematical numerical weather prediction problem is. All right, how did I get in a subject? Okay, we got it entered into memory. Let's get out of this by hitting second mode to quit. Now, ladies and gentlemen, we got to go back to matrix mode. But this time we go over to math. Notice matrix A has been configured as my 3x4. Go over to math. And then we're going to go down and grab this very powerful little function, this little routine. Can you imagine the lines of computer code that are behind the scenes that are going to make this thing do what it does? Somebody has to know how to program this computer. Somebody has to know the underpinnings and the workings behind the scenes mathematically, or else this would never be possible. Ladies and gentlemen, it's the powerful RREF function, the reduced row echelon form function. Hit enter to activate that function. Now we have to type in the name of the matrix that contains our system. We have to go back to matrix mode, but this time stay on names and select matrix name A. Enter. Are you ready for the magic? Get on your mark, get set, go. Boom, done. Solved. Your solution is in the rightmost column. Your X coordinate is -1, your Y coordinate is 7, your Z coordinate is 1. That's your ordered triple solution. Notice this matrix is in what form? Is this row echelon form or reduced row echelon form? What form is that in, ladies and gentlemen?
Reduce.
That's in reduced row echelon form. And we would have had to go on the extra 10 miles to get our matrix into reduced row echelon form. It's amazing. Your calculator did this within about a fraction of a second. Tremendous amount of, what's that?
I have a question.
Yeah.
So after you filled in the columns and then you put second mode, what did you do in between that to get it on? You did matrix mode and then there was a name or whatever.
All right. Well, first of all, do you understand how I entered my matrix into memory? We went to edit, correct? And we established a 3x4. Do you understand that?
Yeah.
Okay, so you got the matrix in memory. Okay, let's say we start from here. Then you get out of this mode once you enter your matrix into memory. Second mode to quit.
Mhm.
Then you got to go back to matrix mode. So second reciprocal X button. But this time you go over to math. And you go down and select the RREF function, the reduced row echelon form function, right there, RREF, not REF, but RREF. Hit enter. Now we got to type in the name of the matrix that contains our system. The matrix was matrix A. How do I get back the name of matrix A? I got to go back to the matrix mode. So second reciprocal X button. And this time we stay on names though, and we select matrix name A. You see that? Just hit enter. There you go. Now you hit enter and boom, the system is solved. Do you see that there?
Yeah.
Does that make sense how I did that now?
Yeah.
Okay. All right, we are pressed big time for time, ladies and gentlemen. Now, the next section, you know what the next section is? The next section is continuing to solve systems using Gaussian elimination. But these systems either have no solution or infinite number of solutions. I am going to show you an example. Just have your eyes right here, ladies and gentlemen. You don't need your calculator now. This system here has an infinite number of solutions. If you were to type the system in your calculator as a 3x4 augmented matrix and use the RREF function, I already did all this, okay, earlier. You know what your output matrix is going to look like? It's going to look like this right down here. This is in reduced row echelon form. Now, look at that last row. The last row of my matrix consists of nothing but zeros. And so this last row is really saying what equation? It's saying 0x plus 0y plus 0z is equal to 0. In other words, 0 is equal to 0. Is this a true or false statement? 0 equals 0. That's a true statement. So you know what? This system has an infinite number of ordered triple solutions. Infinite number. How do we represent those infinite number of ordered triple solutions? Well, we have to choose one of our variables to be what's called a free variable, a variable that can take on any real number value. You know what variable I'm going to choose? I'm going to choose z to be that variable. And so, ladies and gentlemen, if z can be any real number, according to my second row of this output matrix, I would have the equation of 1y minus 2z equals -3. And if I solve that equation for y in terms of z, I would have y is equal to 2z minus 3. So you know what? Z can be any real number, but my y coordinate has to be this. So my z coordinate can be any real number, but my y coordinate has got to be this. In a similar way, my first row of my output matrix generates this equation, of which I then solve for x in terms of z by adding z to both sides, and I get this. So my z coordinate of my ordered triple solution can be any real number, but my y coordinate must be this. My x coordinate must be this. Therefore, this is a way of representing all ordered triple solutions to this system. Z can be any real number. Z is free to be any real number. So my z coordinate can be anything. But whatever my z coordinate is, my x coordinate must be 2 plus that value. And my y coordinate must be 2 times that value minus 3. This is a more accurate way of representing what all ordered triple solutions to this dependent system must look like. Everybody see that there? So how do you know if your system has an infinite number of solutions? If your bottom row of your matrix consists of all zeros, that's how you know your system has an infinite number of solutions. Any questions about that? That's a dependent system.
Even if it's like a 2x2, if the whole bottom
Yep, even
row,
if it was two equations and 2 unknowns, your bottom row would be all zeros for that system, okay? And you would know that you would have an infinite number of solutions. All righty. Okay. Ladies and gentlemen, this is what I want you to do right now, this is not a classwork. This is just something I want you to try real quickly on your calculator. See if you can walk through this routine here. See if you can solve this system of 3 equations and 3 unknowns by entering this in as a 3x4 augmented matrix on your TI-84 and using the RREF function. Go ahead and do that quickly. And we're going to take a look at what the output matrix looks like for this, okay? So go ahead and do this, solve this on your calculator really quickly. We don't have time to do this manually. We're running out of time. But I want you to solve that on your calculator. So this system right here does not have any solution. I think we better take a look and see what the output matrix looks like so that we can understand what it means for a system not to have a solution and what its matrix must look like when you solve it. So enter this in.
How do you clear out the old one?
You know what? You can overwrite it. All you got to do is just go to matrix edit, matrix A, just a 3x4 and just overtype your values, okay? Just overtype them.
Okay, I see it. Thank you.
All you got to do. All right, so let's go ahead and hurry up, solve this using the calculator. So I'm going to do it too here, and we'll compare our outputs here. You can see that I entered the system in to my calculator as a 3x4 augmented matrix, and now I'm about to solve it. Second mode to quit. Go back to matrix mode, math, RREF function. Back to matrix mode, matrix name A. Enter. Boom. There's your solution. All right. Did anybody else out there get this solution matrix?
Yeah.
Can anybody tell me now why this system has no solution? Why? Why is there no solution to this system?
Because 0 does not equal 1.
That's right. It's the bottom row. Look at that bottom row. That bottom row would really give us what equation if we were to transform the rows back into equations. That bottom row, ladies and gentlemen, is going to give me this equation here. It's going to give me the equation of 0x plus 0y plus 0z equals to 1. In other words, it's going to give me the equation 0 because 0 is equal to 1. Is this a true or false statement? That's false. And for that reason, this system has no solution. There would be no solution to this system. Done. Okay? That's all you need to know. So if your bottom row consists of all zeros, you have an infinite number of solutions. If your bottom row, okay, does not consist of all zeros, but you have zeros on the left for your coefficients, and you have some non-zero right-hand side constant, then this system would have no solution. This is called an inconsistent system. So therefore, there would be no order triple solution that satisfies all 3 equations simultaneously. No solution. This means the solution set is empty. Or you could just write the words no solution. All right. All right. In a nutshell, ladies and gentlemen, that's section 6.2. Now, here's what I want you to document. I want you to do this outside of class. This is very, very, very important, because I only showed you 2 examples in section 6.2 that's kind of skimping on things. So I want you got to make darn sure that, and I really shouldn't even have to tell you this, because I should like to think that all of us look at all the examples in all the sections I've been covering anyways. But if you haven't, at least make sure in section 6.2, you study examples 4, 5, and 6. Study them carefully. Very important examples. Okay. All right. I am out of time. Ladies and gentlemen, I have basically shown ourselves an amazing new technique for solving systems of linear equations. It's called Gaussian elimination or Gauss-Jordan elimination, by forcing our matrix into either row echelon form or reduced row echelon form using valid elementary row operations. We covered a lot today, and the only way you're going to simulate all this is by looking at examples in the sections I covered in section 6.1 and 6.2. That'll further solidify what just happened in class here today. And then by starting to do problems, working problems out on your own. And of course, Alex has a beautiful feature where we can click on an example if we get stumped, and it can walk us through a similar example. That's an amazing feature with Alex. Please utilize that if you get snagged on any problem. Okay, so I am going to stay on the line for a couple of minutes. If you have any questions, let me know. Again, on Tuesday, it's review day. I will open up the chapter 5 exam for you on Tuesday. And Alex. All right, have a safe, great weekend.
I have a quick question.
Go ahead.
So when I put that one into my calculator the last time, for some reason I got all the numbers were the same as yours, except for it was decimals at the end, and I don't know like what went wrong in the calculator.